I thought it would be good to give advance notice.
There is also the
Oh,
not next week. I mean that's not next week, the week after in at
right?
university it's called the reading week.
Yes, right.
But it's not this. Is it the 26th or the week after?
No, the reading week I thought was in the period of from February 13, right? To 16 through, yeah, okay, effectively, yeah. No, I'm not teaching in that period. No, no.
That's Thursday. That's not. That has nothing to do.
Right.
For you, it's Tuesday.
Oh, 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 wait. March 12th is not the Udang? Okay, I'm confused. Let's fix that.
Yes.
Well, 12 is a Thursday.
But I think Yudang is 10.
Is the 10? Oh, okay. So in that case. Okay. So let's see. Well, no, it's no problem, but whichever one I should write the correct one. Do you know which one for sure? So I should cancel Tuesday and, okay, so March 10. And is the whole thing should be canceled 3 till 5?
Move an hour but on another Thursday.
Yeah, I will certainly do that.
So for example, yeah.
And that would be, okay. Okay, wait a minute.
That would be perfect.
Okay, so that changed. Good catch. All right, so that means 3 to 5. I think I misunderstood. Okay, so this one is then, where's the cloth? Oh. Okay, so this. So I'll make up with this and this. This works?
Next week.
Yes, that's next week. And then we have the break. And my break goes a little bit longer. I have to return to Indiana for a hiring thing, you know. So we start again at the week of March. Yeah.
The Tuesday.
So it's a long break. And so it will start on the next Tuesday. What is it, March 3rd? That's normal. That was canceled already by Fields for some, I forget, there was a reason. It was needed for another spot. So next week, Tuesday as usual, will be 3 to 5. Thursday, I'm only writing the changes. Yeah, so, okay, so these are some schedule changes. I thought I would put them now. I hope it's not an inconvenience on short notice, but okay. We'll be here. We just have to be here longer. And then, okay, so there are a couple of cancellations. One is for me due to I have a duty in my home university, and then this one is a good one. It's in order that we have a lecture by Udang. Should be very good. And we'll make up on the other days.
So March 5 is just normal. Oh no, it's double.
No, that's doubled, and March 3 is normal. And that's the first one after the break, so it will be a while. Okay, and so I hope, and people online, please take note. It should also be marked on the website now, but I have to, okay, so I have to change the, okay. I have to correct that with Shane. No, that's, yeah, I just have to remember to do this. Okay. Good. Okay, so now, I want to remind you where we finished in the previous lecture. We found that we could compute the essential spectrum, the boundary of the essential spectrum, which is what we need to know. It's a linear algebraic calculation. What is the point spectrum? Well, good question, but there are eigenvalues. We know how to study eigenvalue problems. That's much more straightforward than obtaining resolvent estimates, right? You just find the location of the points, find things that solve a certain problem, and that can be attacked numerically. It can sometimes be attacked by Sturm-Liouville type um, uh, approach, so topological approaches of various types. I'm going to push that off till later. We'll discuss that when we come back from the break, some aspects of studying the point spectrum. But for now, I just want to mention that if you know that you have no point spectrum on the if the point spectrum is also confined to real part strictly negative, then you're okay. You automatically get the uniform resolvent bound that you need. Why? Well, on a bounded set, automatic by continuity of the resolvent and compactness. The resolvent is in fact analytic with respect to lambda, and it's bound. Okay, it's continuous. Therefore, there's a uniform bound on any compact set. So we only need to do large lambda. And this could be done by a damping estimate. The same one that we use to close the nonlinear argument effectively. So let me give you, oops. Exercise would be start with the resolvent equation. And show or compute that, okay, that the real part of lambda, dxv check squared, so the bars are L2 norm, usual L2 norm, okay, which is equal to the real part of dxv against lambda dxv. Okay, now lambda dxv can be obtained by differentiating the equation and setting equal to the remaining terms. If you substitute that in here and carry out integrations by parts, this is the exercise. Show that this is less than or equal to negative some constant times dxv squared plus a big multiple of v L2 squared plus a big multiple possibly of f dxf squared. And if you look at that, it looks like the damping estimate. Lambda is dt, basically. The real part is a little funny, but this is this is the difference between complex and imaginary integration by parts. You have to take a little more care. Okay, and so that gives us a bound like, okay, so we have, this is all good. This could be put over here. This is a good term. And that means for real part of lambda, not too negative. I could move this to the other side and have a positive multiplier. And then over here, I have C dxf squared. That's the resolvent bound I want. I can just take this positive while still allowing lambda to be a bit negative in the real part. And this is my only bad term here. But I claim this absorbs into these two terms. Why or when? Now I use large lambda. Large lambda, going back to the first equation, the undifferentiated equation, I have that a bar dxv is equal to, let's see, no, I want to put that over on, sorry, I want to put that the other way. I have lambda v is less than or equal to, okay, dxv minus dx squared v f. Oops, I need to integrate. Sorry, I need to take the imaginary part. Sorry. Or I need another energy estimate. And now I can keep the full lambda. No, I want sorry, I want imaginary part. This one disappears because it's real. And then I get less than or equal to a big constant times this plus a big constant times that. That's what I need. Now I just divide by imaginary part of lambda. And this is large by assumption.
Is it dpx d square or something?
Square, sorry. Yeah. So this tells me that the L2 norm of V can be absorbed in, it's less than a very small multiple of the sum of dxv squared and f squared. And therefore, I can take this term that I don't want and I can absorb it here and here. Yeah, I can absorb it in the remaining terms, only for lambda large. Here I took imaginary part large. If the real part of lambda were large, I wouldn't even care. It's already absorbable from the first estimate. It's imaginary part that is the trouble. Okay, and there's not actually much to this. It looks exactly like the time evolutionary estimate, and it's kind of instructive to do. This is one standard way of getting resolvent estimates. Usually, you try not to have this term at all. But in this case, it doesn't hurt us because we only care about large lambda. Okay, so to really master this, I would say that's actually a fairly easy case because it's a smoothing operator, it's strictly parabolic. Exercise 2 would be the same, but with the hyperbolic case. And here we would take A bar symmetric and dx of A bar small. If you have those two assumptions, then you should be able to again derive a uniform damping bound, and from that you get a uniform resolvent estimate. And here the key fact is the identity that V against the real part of V against A bar dxV is equal to -1/2 V against dx A bar V. Note, because this is for A bar symmetric. This is real now. So, okay, makes sense. Okay, and this is implied by the real the real valued version, in which case I could just cross out the real here, which says that V A bar dxV is -1/2 V dx A bar against V. And this is the basis of the whole Friedrich's symmetric hyperbolic estimates and theory, because it says it looks like you've lost a derivative in here, but you actually haven't. There's no loss of that. That's how you get around loss of derivatives and get uniform estimates. You can use this directly to prove this. Just break into real and imaginary parts and apply this. Okay, so that's all I want to say. Is it might have seemed like we left out a little something, but actually we didn't. We've completely reduced the question now to studying the eigenvalue problem, so long as the essential spectrum has a spectral gap. Okay, so I'll pause there. That's significant and solves many problems. Doesn't solve the shockwave problem, but that's good. Otherwise, we have no job. Okay. Any questions or discussion on that? That's a leftover. Okay. So now, what do we do about the shockwave case? And I remind you, what is the problem with the shockwave case? The main eraser is over here. This is the one I need. Yeah. Okay, so for shock waves, we have translational eigenvalue at 0. That's not so bad. We have essential spectrum, which is tangent to the imaginary axis. And that is bad. This one we know how to get rid of, right? We basically we can project it out and work on the complementary subspace, even nonlinearly. We showed how to do that. But this one, we can't project it away. It's continuous, and by the Helios-Theta theorem, it prevents exponential decay. That can't be in from this norm to itself. Okay, so I'm going to outline an approach. This is a beautiful work by David Sadinger. Let's see, I think I have the. Let me give the. I've lost the reference, but it's quite early. I feel like it's 76. And then there's the book by Dan Henry, which on behavior of parabolic systems it's from a dynamical system point of view. And I'm basically going from that. This is a really beautiful theory. Okay, so the idea is we think about, again, what's going on here. Which is, okay, we have these The essential spectrum basically has to do with the far field and what's going on there. And what is going on there? In the far field, we have approximately constant coefficient. I'll just write CC, and the equation is dt plus A minus dxv equals dx squared v. And we're doing this scalar case. So this is just a heat equation with a transport term. And in fact, I'm gonna change to this. That's to remind you that it's a scalar, and we have the lax characteristic condition. Now I'm going back to day one. So our shock speed is 0. And it tells us that A minus, the derivative of the flux, is also the characteristic speed. At the hyperbolic level, it's positive. It's moving into the shock. And the characteristic on the right, A plus, must go into the shock. And that's not only from the hyperbolic theory, but from the connection problem for the traveling wave. So this definitely holds so long as we have a profile. Okay, so remembering this. Now, what can I do? Well, I can introduce a different norm that is strategically chosen. So this is called convective stability. That's what we're going to talk about. And it's also sometimes called Sadinger's method of weighted norms. I've heard it called that, but more general terminology is convective stability. And what it takes advantage of is that, well, okay, what does this do? It takes the heat equation basically diffuses things, but the strongest effect is it moves them inward. So let's look at a norm that is going to penalize being to the left. So we look at the norm V eta is defined as e to the minus eta x. Okay, now I'm going to have to choose, I'm going to take x less than 0 here. I have to choose one side or the other to look at, right? They're different. So now I'm looking at the side where we're moving to the right, and x is negative. So this is a positive exponentially growing weight as I go out to the left. Okay, so what happens? As I move to the right, well, not so much happens to this, it's just diffusing, but this part will exponentially decay in time because just by the motion to the right. Okay, and we can quantify, so this looks promising. There, and by the way, the heat equation does not time exponentially decay in L2, because it has the same picture of essential spectrum. It can't. It's roughly bounded. But now in this norm, it should be better. So here's how we find it, and in fact it is. So equivalent is to look at change of coordinates. Okay, so that means, okay, this is what z should be. So I'm looking at v equals e to the eta x z. And if I plug in the usual, so I'm looking at z in the standard L2. But in order to derive the equation satisfied by z, it's more useful to plug this into the v equation and solve. And what we find is dxz will be dx plus eta. dx in the v coordinates will translate to dx plus eta in the z coordinates. This is kind of familiar. So I'll just Yeah, I'll just write it down. So dt plus a times dx plus eta dtz plus this equals dx plus eta squared z. That's the equation. So I can find it kind of synthetically. And more important, I know that if the Fourier symbol for v, so the Fourier symbol is negative ika minus uh, k squared. Then the Fourier symbol for z will just be negative ik plus eta a minus ik plus eta squared. That's the Fourier symbol. And so the question is, what is the dispersion? Oh, this is equal. What is the dispersion relation for this new symbol? And what I'm, whoops. Oh, okay, that was a. Let's take this part. Okay, so it's just expanding a quadratic. So, I mean, we don't even have to look at eigenvalues. It's just simply an expression, and we want to know what it traces out in the plane. Okay, so I want to write it out. Okay, so it's this is the dispersion relation. Lambda of ik is the actual symbol, which is okay, so negative a minus ik plus eta, ik plus eta squared, and then that is negative a minus ik minus k squared. That's the old one. And then what's left over is minus a minus eta plus 2i eta k plus eta squared. And this is the big one. Let's see, this is imaginary. So what I think is I should pick up some extra exponential decay if I do this right. And so let's just see what happens. Well, I get exactly the old dispersion curve, and then there's a shift, and this is positive, and eta is positive, I've assumed. And that makes this a shift to the left. This is good. This one is irrelevant. This one is a square in eta. This is, by the way, this is constant and non-zero. So for eta minus strictly positive and eta sufficiently small, I get a shift to the left. Approximately equal to a minus eta. And it's uniform in ik. There's no k in here. So now my former picture, which was bad, and I'll do the same on the right side, but I'll use the opposite sign. I'll penalize being on the right. And so what I'll get is that the whole thing will shift by, okay, I can use the same, use a combinate, and I can shift the whole thing to the strictly negative half plane. So that's a fantastic idea. It's so elegant, yeah. And it's also really kind of instructive, right? think about spectrum as being kind of independent of the norm almost, but that's the point spectrum. And the essential spectrum is not, because it does involve the spatial features. So I don't know. When I first saw that, I found it really fascinating. That means that for our shockwave problem, okay, what do we want to do though? I said we do the same thing on both sides. What I really mean is you use a weight 8 of x is interpolating smoothly from negative eta for x less than or equal to some large constant, and then positive eta for x bigger than or equal to some large constant, and just smoothly interpolates. Because all I care about is the end states. I don't care about the middle. And my weight will now be my call this a bar to indicate it's not constant. So eta bar weight will be the e to the eta bar. Okay, so we can just do this. It doesn't hurt anything. And the calculations I just did give us the because these have constant limits, because the eta bar has 2 constant limits, all the calculations I did are correct still. They're constant coefficient calculations with the values at plus or minus infinity, and that I was implicitly using that in saying that I can move the norm. So you have to smoothly interpolate. Okay, that's great. So it seems like we're all set, and in fact we are. We can, with this norm, we can now apply the previous theory with projecting out the movement of the wave, the equivariant stability. We get exponential stability of scalar shock waves. There is, however, a detail. It's not a detail at all, but it's one we could easily overlook. We have to look in the nonlinear equation. So in the nonlinear level, we have the z equation. We have dt z plus, okay, L tilde z, and all this is fine. This is what we were just analyzing. But then we have dx of e to the minus eta x n of v. And this is order, okay, n of v. This is like, think of quadratic. Okay, so that's got an e to the eta x z squared, only one of which cancels this, and we're left with order of e to the eta x times some n of z dx. Okay, this would be fine for our analysis. This is fine only if it's exponentially decaying. It has to have a good sign. And the lucky thing is, if things are incoming to the shock, it always has a good sign. So we have eta on the left was, okay. Hopefully that works. Yeah, it needs to be incoming. If it's outgoing, you're fine at the linear level, but you get killed at the nonlinear level. You have an unbounded term. You can't do it. And it does kind of make sense because we're trying to do, eventually things do cross the origin, possibly. And the idea is, well, they don't, because now the inner dynamics somehow kill whatever happened when it reached. This doesn't just keep propagating. The shock processes it and stabilizes it. And if you run some numerics, you can really see this. So at some point, I did a lot of numerics on these, and it's really fun to watch the little signals come in, they hit the shock, and then they disappear. Okay, so, all right, why is that important? Well, it's fine for the scalar shock case, but not for the system case. So it's all, this whole, this series of lectures so far is like the good news and bad news type joke, right? We have, but yeah, so there's suddenly, yes. Oh,
A depends on B. The speed.
Let's see. Well, no, I was putting an A bar. I was putting the background speed into the. So this part has the linear. A depends only on X because it's A of the profile, which depends. But it is A of a, yeah, it is A of V. Yeah, ultimately.
That means that it's has discontinuity.
No, because we have the parabolic term. We have, this is a viscous shock. And so it actually transitions over an extended layer, sort of an indeterminate layer. It's constant far out toward minus infinity, far out toward plus infinity, but in between, it looks like this. And we saw, if the viscosity is of order epsilon, the width of the shock is of size epsilon. Here, the viscosity is 1, so it's just some order of 1, and we don't really see that. Maybe.
Where do I see that?
Where do you see that it's incoming to the shock? From the traveling wave existence problem. We saw it. Yeah, and we also saw it from standpoints of entropy increase, like at the inviscid level. We saw that the one we think should be good is the one that's incoming, just from a point of view of consistency with of the hyperbolic theory and well-posedness. But I mean, that actually doesn't give anything directly for the viscous problem. But luckily they match. It's very nice that they match. Sorry. Yes, the background wave. Yeah, but this is my next comment. So this is the bad news now. So that was the good news. We completely, thanks to Sattinger and Henry and these guys, we completely wiped out scalar shock waves. It's fine. We can do exponential stability again, by being smart.
Different sign for the A minus B plus.
Yes.
What happened in the middle? Do you have to do something?
Well, the A minus and the A plus are just, those are the limits. Yeah, so in between, well, I don't worry in between because really this computation I only do at the end, at the limiting end stage. It's just a computation of the essential spectrum. So what I did is let my weight, so I have an exponential weight with coefficient eta. I just take an eta of x and now let it depend on x in such a way that the value at minus infinity is the one I want, corresponding to the incoming, and the one at plus infinity has the opposite sign, which will stabilize things coming in with a negative, coming into the shock, meaning negative speed.
Because the essential spectrum depends only on this behavior far away.
Right, only on the actual limiting behavior. So in between, I can do whatever I want. Yeah. Right. Which is strange. Also, I mean, this stuff is really, it's kind of through the looking glass or something. Yeah, these are very powerful principles. Okay, but now the system case. I'm going to talk about this after the break. So in March. So I have a little delay after these. But one thing I will tell you is it's not so hard to figure out the lax characteristic condition. Says that, well, okay, let's just take simple case. The number of incoming characteristics must be equal to n plus 1. And that means the number of outgoing is n minus 1, where n is the dimension of the system. Why? Because n conditions, the Rankine-Hugoniot conditions. This is all at the inviscid level, by the way. So now I'm not, and it actually can be related to the traveling wave problem again, but that's another story. That's a little harder. So I'm just going to, give a heuristic comment. We have n conditions. What are our unknowns? Well, from incoming waves, that's no problem. Viewing this as a boundary transmission type problem, that's our data, the waves that come in. And we need to determine values for the waves leaving and for the speed of the, it's actually a free boundary. So n minus 1 out plus 1 speed. The speed of the disk of the free boundary, which is the shock. Or little n is the dimension of the variable u in the problem, the number of variables. So the number of characteristics. So here I've drawn n equals 2. So I have 2 characteristics on the left, 2 on the right. And the Rankine-Hugoniot conditions look like, just to remind you, it says the jump at the shock. So this is defined as the difference between the rightmost limit and the leftmost limit of the variable u should be equal to the jump in the flux f, where my problem is dt u plus dx f of u equals 0. That's the background equation. This would be then, yeah, this could be this at the inviscid level. So I didn't put any viscosity. This, it at least makes sense. Yeah, it's well posed. It's the right number of, I have the right number of variable unknowns and conditions. Of course, that's a linear, that's a linear algebra problem. It's not enough that I have the right number of variables. There's a determinant condition in there too. And that's what we're going to talk about after the break, things like this. How do but okay, so there's some additional condition, but basically you at least need this or you're sunk. This is like consistent splitting. I would say in fact, it's exactly consistent splitting. But for the hyperbolic inviscid case, as opposed to the consistent splitting that we got for second order systems for the viscous case. But it's along that line. You couldn't solve, if you wrote down a resolvent problem for this resolvent equation, you wouldn't have the right number of variables to solve uniquely. Okay, so, all right, so what's my point? For n bigger than 1, we have O bigger than or equal to 0 outgoing, bigger than or equal to 1, sorry, outgoing waves. So this convective stability depends on things convecting inward, because otherwise, at the nonlinear level, we have a problem. And I should say, it's not always insurmountable. People have done analyses like that, where they use some other information to control things. So this is basically a problem that I have z squared. If I write this as z squared, I have this left over. But what if I write it as z times u? And what if I have control of the u norm by other means? This would actually be okay. That's a very side comment, but Pago and Weinstein made good use of that observation in the
classical P system and.
yes. Yeah, so for the isentropic gas dynamics P system, yeah, the simplest one, I already have a problem because it's n minus 1 outgoing. Okay, so when n was 1, the scalar case, that's 0 outgoing waves, and we're in great shape. But that was just an accident of the dimension. For all higher dimensions, there's at least 1 outgoing, and often many. So this doesn't work. So we have to do something else. Okay, so So we've done scalar, we want to go to systems, or we want a method. I'm going to show you the method for scalars, but the method that will work for systems. Because, yeah, we don't want to do all the bookkeeping for an entire system, but I'll do the scalar case next in a way that generalizes. Okay, but first, I mean, any more questions or comments on the convective stability, which is really interesting in its own right. I like that topic a lot. Okay. I did forget to make one important comment. I think the most interesting thing about this is that this technique, it's sort of an open condition, right? I can move, I don't, I move the spectrum an arbitrary, though small, distance to the left. But that means I could also stabilize, I did that to stabilize neutral waves in this case, but I could also stabilize unstable waves. I could take waves that have exponentially unstable essential spectrum, and if it's not too bad, I can use a weighted norm and it can become stable. That is, yeah. Well, this is when okay, so I mentioned I did a lot of numerics of these things at some point. Okay, so here's the background shock. I'm going to draw you a picture of what happens. Okay, so what we always did to test stability is we'd put a little box because we were kind of, lazy. And also we wanted to see things very clearly. So we put compact support always. Okay, so this would, after a while, it would, in good cases, when it was stable, it would form a Gaussian wave packet. Basically, it would come in and then disappear. And out here, if we put another one, okay, same thing. It hits the wave and gets stabilized. That's neutralized or right, eliminated. But what happens in the unstable case? Okay, so maybe you've seen this. The generic unstable behavior looks like this. It's a Gaussian wave packet with oscillations and growing time exponentially, but not without bound. It grows with a certain exponential rate, which would be small if it were just barely unstable. Well, so it's spreading, it's growing, it's also convected to the right. If the convection to the right is fast enough, this reaches the wave and gets eliminated. And you can really do some back of the envelope things and sort of find the border of the invading. It looks like an invading front type problem. And you can really figure out to a pretty good approximation when it is stable and when it's unstable. And stability just means the wave outruns or the shock outruns the instability. Thinking of the shock as moving toward the wave. Okay, but obviously, if I move this far away, that doesn't help, right? It will always lose if I move it far enough. So what I have to do is by putting a weighted norm, I say, okay, I'm allowed to put things far away, but only very small things. And that's exactly and so that delays the growth just enough so it always kills it. And you can see it very clearly. And then, so I don't know, for me, this is so concrete that I can understand the mechanism. When I just see essential spectrum moving by magic, I don't understand it.
It's the way you measure perturbations and but the way you explain it, it's a bit hard for me. But
Well, I'll just say that I think it's clear if you think about the movement of the waves and what the signal, so the signals are growing, but they're also moving, and just do like approximate computations. That tells a lot. That's the way I understand it. Okay. So, all right. So what we're going to do instead is, okay, so we can't rely on convection. Convection can restore exponential decay. That is asking too much. Instead, thinking of the outgoing waves, we're going to do what's called diffusive stability. And some references would be actually Schneider in 95 kind of coined this term, and in the context of periodic solutions, but the techniques, Matsumura and Nishida, 83, I think. I mean, it was being done long ago, but this took this nice term and ways of looking at it. I feel like Schneider clarified some things too. So, and many others. So the idea is, okay, here is the idea. dt plus a dxv equals dx squared v, same equation, a positive. And now on the whole line. So I'm not going to just rely on the fact that I'm going one way. I'm just going to ask, what can I get without? Yeah. Well, this can't help me then at all because of translation invariance. The only thing that can help me is basically this, which is diffusing things. And the way I'll see that is I'll use the solution formula by the green kernel or heat kernel. So we have e to the LT v naught of x is the integral from minus infinity to plus infinity of the green kernel, x minus y, v naught of y dy, and g of z is e to the minus z squared over 4t over square root of 4 pi t. So we know very explicitly what's happening. Okay, so now what we're going to use is we can also write v of t is g star v naught. G of t star v naught is suppressing the x. It's just a convolution. So I'm going to recall Young's convolution bounds, which say for 1 less than or equal to q r p less than or equal to infinity, 1 over q plus 1 over r equals 1 plus 1 over p. We have that we can bound the convolution of f and g LP norm by the product of the LQ and LR norms. So that's a kind of standard one. And so if p equals infinity, that's just Holder. What are some other ones? Q equals 1 is just triangle inequality. Looking at what these are. Okay, but anyway, these are true in general. There you know them. Yes.
You remove transport term by.
Oh, I'm very sorry. I did remove. Yeah, I removed the transport term. I didn't mean to do that. It's x minus z minus a t squared. Thank you. Yeah, I didn't mean to do that. No, I'm not changing coordinates. Okay. So here's our lemma then that we want. We want some bounds. And so the bounds are, or the lemma is the LP norm of G in X is less than or equal to a constant, T to the minus 1/2, 1 minus 1 over P. And the derivative It's bounded by C times T to the minus 1/2, 1 minus 1 over P minus 1/2. So you get an extra 1/2 time decay for each derivative. And well, substitution or scale invariance of G. G has a scaling invariance in X over square root of T. Or let's see, should be X minus AT over square root of T. That's the variable we want. We plug that in, compute, you get something that has no T. You have this factor out in front of an integral that clearly converges and has no T. An exponential in Z, which goes into the constant. Yes.
Why 8? Is 8 come?
Oh, infinity. Sorry, P equals infinity would be, oh, wow, that's, well, sorry, I don't know. It's supposed to be, let me try even one more time. Yeah. Man, there's no, yeah, rotation invariance. All right, so I'm going to skip that for time, and then we get corollary. E to the LT V naught in L2 is less than or equal to V naught. L1 intersect L2, so I mean the max of the two norms times a constant 1 plus T to the minus 1/4 and E to the LT V naught dx, the derivative of the solution in L2 is bounded by a constant 1 plus T to the minus 3/4 B naught L1 intersect H1. And the proof is the Young's plus the lemma. But to be determined. I'll leave that because I know there's a talk following the lecture, so I should not go over. And the proof is very quick, but I don't want to go over. We'll restart here. But you see what we get. It's not at all what we're used. We had exponential decay. We had a giant hammer to work on our nonlinear decay. Now we have only just a little bit of diffusion. Why is it called diffusive stability? Well, you see, because I assumed localization of the data. It's kind of like a weighted norm, but it's very weak. And then that spreads out and causes L infinity decay. We can basically see, let's see, yeah, well, in all higher norms, it gives you a little bit of decay, anything higher than L1. In L1, so if P, let's see, so if, well, I didn't do L1, but had I written it, it would have been just 1. It wouldn't be decaying at all. Okay, but, all right, so I'm going to stop here without proving this last part, but the statement is the bounds we get, and these are sharp, by the way, are just algebraic, but they are something. And again, this is not an ODE type result. We've left ODE now. We're very much using the spatial effects. We did it in the weighted norms. Here we're doing it in this idea that localized data gives decay in higher norms. So L1 localization gives LP decay. This is constant coefficient, but even that, is, I mean, it's a little bit delicate. Yeah. And yeah, I'll give a nonlinear argument next time, and you'll see that, it doesn't always work. The nonlinearity has to be, well, it has to be a sufficiently large product. So if I had n to the v to the second, that wouldn't work. If I have dx v to the second, it works. If I have v to the third, it works. But it's delicate, yeah.
Distinction between this estimate, which is algebraic,
Mhm.
and the previous one, the translation of the spectrum, which into potential gain.
Well, you could think of it this way. Let's see. So if I had done, what if I did an algebraically weighted norm? That's an interesting, and people have done that. Then I get algebraic decay from convection. And it would be basically, if I have like 1 over x decay, I get 1 over t decay. It says something like this. It's directly,
And in the other case, you have the exponential decay.
yeah, and it translates to exponential decay in time. But here, I'm not even assuming, I'm not assuming algebraic decay at all. I'm just assuming L1. And I could be more, I could get more precise bounds if I assumed a certain algebraic rate. But this is what, yeah, but for a nice clean argument, this will work. Just L1, turns out. And yeah, and so what would I expect? I would expect something like, well, from the convection, if it were L1, it's kind of like maybe a weight of x, right? To make it 1 over x, almost integrable. It's sort of like that. And so maybe I would have a 1 over t decay, perhaps, from convection. But I'm not getting that. I'm getting 1 over square root of t decay in the L infinity norm. Basically, if you if you want to know the decay of L1 data, just look at the lemma. Where did it go? The LP norms on G. That's basically the classic solution to L1 data. And you see, when P is infinity, I get t to the minus 1/2. When P is 1, I get C. So L1 to L1, nothing. L1 to L infinity, you get t to the minus 1/2, and it interpolates. This is optimal. Yeah, yeah. It's optimal because actually this is why. Because if I do take a delta function data, I get exactly G, and the G ones they're solid. It's equal. It's not unbound. It's equality.
There's some estimate assuming only V0 in L2.
Yeah, this estimate is no V0 has to be in both L1 and L2, and I'm mostly using L1. This is the key. L2 I use only to get rid of, you see, I don't like the t, and for large time I like t to a large negative power, but for small time I don't like it. Now it's blowing up. So I want just a 1 here. Well, that I can get going from L2 to L2. I have a nice bound there for the heat equation. I just have a, yeah, you interpolate between the two. Or just divide into 2 cases, right? For t less than or equal to 1, I'll use 1 estimate, L2 to L2, the trivial one. And for t bigger than or equal to 1, now the 1 plus t and t are effectively the same. They're comparable. So I'll use now the L1 to L2 bound on that range. And that's the strategy. Yes, but I'll give the proof and you'll see in the next lecture. And then we'll go on to see, well, yeah. So what we want to do, I mean, this is great because we had the green kernel. We had something very explicit, and we don't up to now have that at all for the shockwave problem. But the point is, we're going to get green function estimates that allow us to do things like this. And that's the trick. Okay, so I think I better stop there.